Welcome, gentle listener, to Sleepy Facts. Here in the quiet spaces between seconds, knowledge unfolds not as a lesson, but as a slow, soft light. This is a place to rest your mind, to let the weight of the day dissolve into the gentle hum of the cosmos. Tonight, we will listen to one of its oldest rhythms, a story that is always turning just beneath the stillness of the world. So find a comfortable place, let your breath deepen and feel the stillness around you. It is a quiet so profound it feels as if the universe is holding you in its palm, unmoving, unchanging. The air does not stir. The stars do not tremble. It is as if you are frozen inside a perfect, silent moment. But what if this stillness is the greatest illusion of all? What if it is a soft blanket covering an endless, silent motion? A cosmic dance that began before the first light, before the first memory. Tonight, we drift into that mystery. We follow the turning of everything from the smallest atom to the widest swirl of a galaxy. And we listen to the silence that is not an absence of motion, but the sound of everything moving together. In this moment, as you breathe, the earth is turning. A steady, silent spin of over 1,000 miles an hour at its equator. It is a speed too vast for our senses to hold, a motion too smooth for our bodies to feel. And as it turns, it is also rushing through space, orbiting the sun from 93 million miles away. A journey it makes at nearly 67,000 miles an hour. Yet the coffee in a still cup does not ripple. The air in a quiet room does not drag, and the journey widens. The entire solar system, with our Earth held safely within it, sails around the heart of the Milky Way galaxy at a speed of almost 500,000 miles an hour. And still, we feel nothing. Our heartbeats do not tremble. Our breath does not sway. We are passengers on a vessel of impossible speed. Yet we are wrapped in a profound and gentle calm. This is the great paradox of our existence, the quiet meeting of motion and stillness. From the smallest electron humming in its orbit to the largest gathering of galaxies, twisting in slow rivers of light, everything spins. Atoms rotate, planets revolve, galaxies twist in silent, spiraling dances of dust and stars. Some even believe the universe itself has a faint global rotation written into its very fabric, a memory of its first breath. But why? If everything is in motion, why do we feel so perfectly still? The answer is a quiet one. It begins with a principle in physics that is as powerful as it is soft. A law called inertia. It was first described in the 17th century. A simple and elegant truth An object in motion stays in motion unless something else pushes or pulls it. This is the secret to our stillness. We do not feel the earth's endless turning because we are moving with it, not against it. Your body, the air you are breathing, the oceans and the mountains, all of it turns together, locked in a single, silent, ancient rhythm. To feel motion, there must be a difference, a change, a push or a pull. But here, there is no change. The earth's spin is constant, a smooth and seamless glide that has remained the same for longer than human memory. Astronauts too feel this illusion on a much grander scale. In orbit, they circle the planet at 17,500 miles an hour, seeing a sunrise every 90 minutes. Yet, inside their spacecraft, everything is calm. Without the friction of air, without resistance, their incredible speed feels exactly like stillness. This is the nature of uniform motion. It is the same gentle law that allows you to be on an airplane traveling 500 miles an hour and feel as if you are sitting perfectly still. You and the plane are moving as one. Only when there is a change, a moment of turbulence, do you feel the movement. The Earth's motion is seamless. There are no vibrations, no friction, no sudden shifts. And because space is almost a perfect vacuum, there is nothing to rush past us. Nothing to remind us that we are spinning at cosmic speeds. It is easy to forget because our senses were not built for such scales. Our inner ears, which give us our sense of balance and motion, evolved to navigate the small movements of life, walking, running, climbing. They are designed to respond to acceleration, to a change in speed, not to a steady, constant velocity. It is why you feel the gentle push when a car starts to move, but not the speed of its cruise down a quiet highway. On Earth, everything moves with you. There is no start or stop, only an eternal, silent gliding. And yet, we can see this hidden motion if we know how to look. In 1851, a physicist named Léon Foucault hung a heavy pendulum from the dome of the Pantheon in Paris. As it swung freely back and forth in a straight line, the floor of the great building slowly, imperceptibly turned beneath it. The pendulum itself was not twisting. The earth was. If you have ever stood beside one of these pendulums in a museum, you have witnessed the earth's rotation made visible, a silent, graceful dance where time and motion meet one gentle swing at a time. On a cosmic scale, this rotation is everything. The Earth's spin is what creates day and night. It is what stabilizes our planet's magnetic field, an invisible shield that protects all life from the harsh radiation of the sun. Without this constant turning, our world would be a desolate place, one side scorched by endless daylight, the other frozen in eternal night. Our planet's spin is not just a motion. It is the engine of our world, a delicate balance that allows life to exist. Even this stillness is not permanent. There is change, slow and invisible, but real. The gentle pull of the moon's gravity creates the tides, and this friction has been slowing the Earth's rotation over billions of years. Each century, the length of a day grows longer by about 1.7 milliseconds. It is a change too small to notice in a lifetime, but it is a reminder that even our planet's rhythm is slowly, softly unwinding. When we look deeper, we see that rotation is not just an earthly phenomenon. It is a cosmic signature, a pattern written into the heart of everything. Stars are born from vast collapsing clouds of and dust. As these clouds shrink under the pull of gravity, they begin to spin faster and faster. It is the same beautiful law that makes a figure skater spin faster when she pulls in her arms, a principle called the conservation of angular momentum. Every planet born from that swirling disk of stardust inherits a piece of that motion. The Earth's 24-hour day is a fossil, a preserved trace of that ancient creative whirlpool. Even the sun spins, turning once every 27 days, dragging its glowing magnetic fields through space like threads of light. And our galactic home, the Milky Way, turns once every 230 million years, carrying hundreds of billions of stars in a slow spiral dance that began long before our world was even formed. With instruments like the James Webb Space Telescope, we can now see galaxies so far away that their light has been traveling for over 13 billion years to reach us. And even in those first primordial galaxies, we see the telltale signs of rotation. A gentle hint that the tendency to spin is written into the universe's DNA. How then can everything be in such constant motion and yet feel so perfectly still? Part of the answer lies in the soft flowing nature of reality itself. According to Einstein, there is no absolute motion, only motion relative to something else. From our perspective, here on Earth, we are at rest, and it is the universe that turns around us. From another perspective, out in the deep quiet of space, the opposite is true. Both are correct. This beautiful symmetry is what makes our stillness an illusion of perspective. We are passengers so perfectly adapted to the calm, steady motion of our world that we no longer notice the journey. Our stillness is a form of survival, a balance between what our senses can bear and what the cosmos demands. If we could somehow feel the turning of the Earth, the pull of the sun, the slow drift of the galaxy, our perception of time itself would unravel, because motion and time are woven together. The spin of our planet defines our days and years. It is the quiet heartbeat of the cosmos. The quiet you feel now is not the absence of motion. It is the harmony of everything moving together. So when you lie down tonight, beneath the invisible turning of the stars, remember this: you are not standing still. You are gliding through a cosmic river, gently, constantly, endlessly. Each moment of stillness is just the universe moving too smoothly for you to notice. In that perfect balance of motion and calm, life finds its quiet rhythm. Take a slow breath. You are spinning. You always have been. And the silence you hear is the sound of everything moving together. This quiet journey drifts deeper now backward in time to a moment before motion had a name, when the universe itself took its first gentle turn. If you could turn back time, not just centuries or millennia, but all the way to the first second after the beginning, what would you see? Would there be light? Would there be sound? Or would there only be a sudden gentle motion, a swirl, a twist? The very first rotation of everything that would ever exist. The question of what gave the universe its first spin is not one of philosophy, but of physics. The answer lies buried deep within the quiet equations of cosmology, inside the earliest moments of time, when matter, energy, and space itself were just beginning to unfold. It is a time astronomers call the blank era, a window so early within the first fraction of a second that our current laws of physics become like whispers, unable to fully describe it. But what little we can sense from that distant shore suggests something extraordinary. The universe may have been born not in perfect stillness, but in a gentle, turning breath. Today, scientists can listen for the echoes of that moment. They study the cosmic microwave background, the faint, ancient afterglow of the Big Bang detected by satellites drifting in the silent dark. This soft light, which fills all of space, carries a memory. Within it are tiny irregularities, small ripples in temperature, only a few millionths of a degree apart, like the faintest breath on a still lake. These patterns tell us that the early universe was not perfectly uniform. There were slight differences, and those differences over billions of years grew into everything we now see. They became the seeds of galaxies, of stars, of planets, and of life itself. But some researchers notice something stranger within these patterns. A faint alignment. A kind of large-scale twist in the way those ripples are distributed across the sky. It is a mysterious signature, a hint that the universe on the largest of scales might have a preferred direction of rotation. If it is true, that first faint spin could have shaped everything that followed, from the slow spiraling arms of the galaxies to the very flow of time itself. How could such a rotation begin? The key might lie in the quietest, most subtle of places, in quantum fluctuations. These are tiny, random shivers in energy that occurred when the universe was smaller than a single atom. Even in complete, perfect emptiness, these fluctuations happen naturally. The quantum fields that weave through realities are never perfectly still. They jitter. When the universe was born, those imperceptible jitters were suddenly stretched and amplified by a brief but explosive expansion called cosmic inflation. In a moment, the universe grew faster than the speed of light, and that rapid stretching could have turned some of those quantum jitters into gentle swirling motions. The first cosmic spins. Theories of inflation explain why the universe appears so smooth and uniform, yet still contains the seeds of all we see. But in recent years, observations have suggested that during this expansion, subtle rotational patterns may have been imprinted on the first gravitational waves. Tiny curls in the fabric of space-time itself, a fossil record of the universe's first turn. They suggest that the beginning was not just an explosion outward, but a twisting birth one that imprinted the memory of spin across every scale of matter. And this makes sense when we look at what happened next. As the universe expanded and cooled, matter began to form. Each particle carried with it a tiny amount of this inherited motion, this angular momentum. When gravity later gathered these particles into vast clouds and then into galaxies, that ancient angular momentum was conserved. It is the same quiet law that makes a figure skater spin faster when she pulls in her arms. In physics, nothing spins from nothing. Motion must come from motion. And so, the first spin, however small, had to exist from the very beginning. Astronomers today can see the fingerprints of that rotation in distant galaxies. By analyzing thousands of spiral galaxies, they have found a subtle preference in the direction they turn, an imbalance that might trace all the way back to the early universe's spin. While the evidence is still soft and unfolding, this handedness of the cosmos hints that our universe may not be entirely random. There may be a hidden rhythm, a silent turn that everything still follows. Even dark matter, the invisible scaffolding that holds galaxies together, seems to carry this spin signature. In computer simulations, we see that dark matter halos twist and rotate over billions of years, guiding the visible galaxies within them, like gentle whirlpools guiding leaves on a stream. Without that slow, steady rotation, galaxies would tear themselves apart. It is as if the early universe set everything spinning, and now The echo of that first motion is what keeps the stars in balance. Still, the quiet question remains: who or what began the spin physics offers a gentle answer: symmetry breaking. In the earliest fractions of a second, the forces we know today were once united a single perfect whole. But as the universe cooled, they began to split apart. When that perfect symmetry broke, tiny imperfections appeared. Those imperfections are what allowed structure, motion, and spin to exist. In a perfectly balanced universe, nothing could move. But a slightly unbalanced one, it could dance. We can see this principle mirrored everywhere. In the way some particles have a left-handed preference, in the way atoms rotate. Nature, it seems, is not perfectly symmetrical. And that tiny, beautiful flaw is what allows everything to turn. Some scientists have even tried to listen for the rotation of the entire universe. By analyzing the light from hundreds of thousands of galaxies, they have found that galaxies in one half of the sky seem to rotate more in one direction than the other. This does not mean the cosmos is spinning like a top. Rather, it might mean that the fabric of space-time itself twisted slightly during its expansion. Even a subtle twist could cascade across billions of light years. A collective pattern of motion, a preferred direction that began in the earliest moments of the universe. To us, it feels invisible, but on a universal scale, it could shape the geometry of everything. Even on the smallest level, spin is fundamental. Every particle, electrons, protons, neutrons, carries an intrinsic spin. It is not the kind of spinning we imagine, like a tiny turning ball. It is a deeper quantum property, a mathematical rotation encoded in its very being. As one physicist said, a particle does not spin. It simply has spin, just as it has mass. Rotation was not added to the universe later. It was part of the blueprint of existence. So when you look at the night sky, you are seeing the inheritance of that first motion. Every galaxy's swirl, every planet's orbit, every photon of starlight, all descend from that first cosmic rotation. Without it, matter would never have gathered. Stars would never have formed. And time itself would have no rhythm. Motion is not an accident of the universe. It is its heartbeat. And though we may never know exactly what triggered that first spin, the evidence keeps whispering that it has always been there. Quiet, steady, invisible, yet written into everything we can see. The universe never had to learn to move. It was born already in motion. The spin was not created. It was inherited. Take a breath. The atoms in your body too are still turning with that first impulse. From the tiniest electron to the swirl of the Milky Way, the same rotation continues, unbroken, a quiet current flowing through 13.8 billion years. We are not separate from that motion. We are its continuation. And as this motion continues through us, it also flows around us, shaping the very world we call home. Without rotation, the earth would be silent. There would be no day and no night, no weather, only a world of sharp, brutal contrasts. One side turned forever toward the sun, a scorched and silent desert. The other side turned away, frozen in an endless starlit darkness. A dead world adrift in light. But because it spins, this planet breathes. Every sunrise is a note in its long, slow rhythm. Every wave that curls upon the shore, every gust of wind that moves through the trees, they all come from the same ancient turn that began 4.5 billion years ago. The Earth's spin is not just a motion. It is an engine, a delicate balance that sustains everything we know as life. From the invisible shield that protects us from cosmic radiation to the cycles of warmth that nurture oceans and clouds' rotation, shapes our world in ways we can see and in ways we can only feel. Our planet's steady rhythm sets the pace for everything. Every plant, every animal, every current in the ocean is synchronized to it. It is an invisible metronome ticking softly beneath everything that is alive. The first and most gentle consequence of this rhythm is the turning of day into night. This simple alternation distributes the sun's warmth across the surface of the world, creating the gentle differences in temperature that drive the wind, the currents, and the weather. Without that daily rotation, the boundary between the light and dark hemispheres would be a violent, unlivable wall of storms. But because the earth spins, the sun rises and sets, and its energy is shared, allowing for stable climates, for gentle seasons, for a world where life can find a quiet place to grow. Rotation also awakens our planet's heart. Deep beneath our feet, the Earth's core of liquid iron moves and churns. And this motion generates a vast, invisible magnetic field. This field is our most crucial shield. It flows out from the poles and wraps around the planet, deflecting the solar wind, a constant stream of charged particles that flows from the sun. Without this shield, those particles would slowly strip away our atmosphere, leaving the world exposed and barren. We can see what happens when this protection fades. The planet Mars spins at almost the same rate as Earth, but its smaller core cooled long ago. Without the motion of molten iron, its magnetic field vanished, and its air was slowly carried away by the sun's radiation, leaving behind a dry, frozen desert. Here on Earth, our magnetic field still holds, and it gives us a gift of gentle light. The auroras, those soft glowing curtains that shimmer near the poles, are not just beauty. They are proof of our planet's protection. They are born where the magnetic field bends and touches the solar particles. A soft reminder that our planet's rotation still powers an invisible force field all around us. But the spin's influence does not stop there. It also governs the air itself. Because the Earth turns, air moving through the atmosphere does not travel in a straight line. It curves. This gentle turning creates the vast spiraling systems of winds and currents that define our weather. It is why hurricanes spin in their slow, powerful dances. It is why great ocean currents carry warm and cold water across the globe, balancing the world's temperature. Without this effect, weather patterns would collapse. The delicate systems that bring rain to the forests and cool breezes to the shores would simply cease to be. The speed of a planet's rotation shapes its soul. A world that spins too slowly, like Venus, can trap heat until its surface becomes a furnace. A world that spins too quickly, like Jupiter, can be torn by ferocious, planet-sized storms that rage for centuries. Earth's 24-hour rhythm is a near-perfect tempo. It is long enough to distribute energy, but short enough to prevent any one place from growing too hot or too cold. And to this perfect rhythm, life has learned to listen. Every living thing on Earth carries an internal clock, a circadian rhythm that aligns with the planet's rotation. It is a molecular timekeeper, a quiet pulse inside every living cell that connects it to the turning of the world. This rhythm tells the flowers when to open their petals, the birds when to migrate, and us when to rest. If the Earth were to stop turning, this deep biological harmony would shatter. Rotation even shaped our closest companion. Billions of years ago, when the Earth was young, it collided with another world. The impact sent a cloud of debris into orbit, which slowly gathered to become the Moon. That great collision also set the Earth spinning much faster than it does today. Over eons, the Moon's gentle gravity has been pulling on the Earth, slowing its spin and gradually lengthening our days from just a few hours to the 24 we know now. This slow gravitational embrace keeps our planet's tilt stable, preventing the kind of extreme climate swings that would make life impossible. The same tides that shape our oceans are a reminder of this ancient connection, a quiet conversation between the Earth and its Moon. When we look beyond our own world, we find that rotation plays a similar vital role everywhere. It is a fundamental ingredient for a habitable world. It shapes a planet's day, its temperature, its atmosphere, its weather, and its safety. Life, it seems, thrives not in spite of motion, but because of it. The rotation of the Earth is the quiet architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, into you. And as we drift deeper into this journey, we follow that rotation outward to a place where spinning no longer just shapes life, but begins to bend something even stranger. A place where rotation does not just move matter, but begins to twist time itself. When rotation reaches its limit, it stops being just a motion and becomes a distortion. At extreme speeds, a turning object no longer simply moves through space. It begins to pull at the fabric of time itself. It was Einstein who first understood this deep connection. In his vision of the universe, gravity and motion are inseparable, two quiet expressions of the way mass and energy curve the geometry of space-time. The greater the spin of an object, the more it twists the world around it. This gentle twisting of space-time is called frame dragging. It is one of the most subtle and beautiful predictions of modern physics. Imagine space-time as a perfectly calm, silent lake. When a massive object like the Earth spins within it, it stirs that lake, creating tiny, invisible vortices in the very flow of time. In these quiet whirlpools, the direction of time itself can begin to curve. It is a motion so faint, it seems impossible to measure. Yet we have a mission called Gravity Probe. Launched in 2004, used 4 of the most precise gyroscopes ever made, and watched them as they orbited high above the Earth. After a year of silent observation, the mission confirmed that our planet's rotation does in fact drag space-time with it by the smallest of fractions. It was an amount so tiny, it was like measuring the thickness of a human hair from 100 miles away. But it was there. Even our gentle planet, turning once every 24 hours, is capable of bending the flow of time. Now imagine a rotation billions of times faster and a gravitational field billions of times stronger. That is what happens near a neutron star. When a massive star dies, it collapses under its own weight, squeezing its matter so tightly that a star larger than our sun becomes a sphere only a few miles wide. To conserve their ancient motion, these stars spin at unimaginable speeds, sometimes hundreds of times every second. We see them as pulsars. Their magnetic poles, sweeping beams of light across the cosmos like great cosmic lighthouses. As they rotate, They twist space-time so violently that even light struggles to travel in a straight line. Near a pulsar, time itself ticks more slowly. The stronger the spin, the slower the clock. This is not magic. It is the quiet logic of the universe. Time runs more slowly in places of stronger gravity or faster motion. When you are close to a massive spinning body, space-time itself is pulled into its rotation. You cannot stay still. You are dragged along as if the universe itself is turning you. This effect is most extreme near a spinning black hole. A Kerr black hole, as it is known, is perhaps the most exotic structure in the universe. Unlike a simple, non-rotating black hole that only pulls things inward, a spinning black hole twists space-time around it like a vast, invisible whirlpool. Close to its edge at the event horizon, the speed of that rotation approaches the speed of light. Nothing, not even time, can resist being dragged along. The region where this happens is called the ergosphere. Within it, nothing can remain still. Every particle, every photon of light must rotate with the black hole. It is as if space itself becomes a liquid caught in an inescapable spinning current. Inside that whirlpool, time behaves differently. If you could hover there, your clock would tick much more slowly than a clock back on Earth. For every minute you experienced, hours or even years could pass for the rest of the universe. We have seen this. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow. That luminous glowing ring we see is not light from the black hole itself, but from matter spiraling around it. Its path bent and its time delayed by the warped geometry of space. Those glowing arcs are visual proof that rotation and gravity together can bend not just light, but the very flow of time. These laws apply on smaller scales too. Even the satellites that orbit our Earth experience tiny differences in time. The Global Positioning System, or GPS, must constantly correct for the fact that the clocks on its satellites moving fast and in weaker gravity tick just a little faster than our clocks on the ground. The difference is only a few millionths of a second per day, but if left uncorrected, it would be enough to make our maps useless within hours. So every time you find your way with a phone, you are witnessing this quiet truth. The bending of time is not a distant theory. It is part of our daily lives. In the most extreme environments near a spinning black hole, the mathematics of space-time becomes breathtaking. Rotation can twist the geometry so sharply that paths can appear where it is possible in theory to loop back to an earlier point in time. Whether these loops are real, we do not know, but they emerge naturally from the equations that describe our universe. In these places, the ideas of past and future lose their fixed meaning. Rotation, it turns out, does not just shape matter. It defines how time flows. The faster and denser the spin, the greater the warping of space-time. From our gentle planet to the violent hearts of distant galaxies, the universe uses spin to sculpt both motion and time. What we call now is different everywhere depending on how fast and how deep the local space-time is turning. The universe does not just move through time. It creates it through motion. Every spin, every turn writes the seconds we live in. And if rotation can bend time, what happens when time itself begins to control the spin? That is the mystery waiting in the stillness ahead. Every second you live is shaped by this quiet motion. The most reliable keepers of time we have ever known. The atomic clocks do not measure the turning of a world, but the whisper of a single atom. Inside them, electrons whirl around a nucleus held in place by invisible forces. When they move between these precise orbits, they release a tiny pulse of light at an exact frequency. That frequency, a quantum hum from the heart of a cesium atom, is what defines the length of 1 second. Every moment of your life is calibrated to this tiny, perfect atomic spin. This is a different kind of turning, not a physical twirling, but a fundamental property of matter, an internal rhythm that every particle carries. This quantum spin is what determines how atoms behave, how they connect to form the world, and how they arrange themselves into the substance of life. At its smallest, most fundamental scale, our measure of time depends on this silent internal motion. But just as the atom's spin governs our smallest measure of time, the planet's spin governs the rhythm of our lives. The Earth's rotation defines the length of a day, and its long, slow orbit around the Sun defines the length of a year. And these motions are not fixed. They are alive, and they drift. The gentle pull of the moon in its slow, silent conversation with the Earth is gradually slowing our planet's spin. Each century, the day grows just a little longer to keep our perfect atomic time and our planet's drifting natural time synchronized. We sometimes add a single second to our clocks, a leap second. It is a quiet admission that we are constantly recalibrating our human time to match the Earth's cosmic breath. This connection between motion and time is not just a theory. It is a quiet current running through our world, a current so gentle it is nearly impossible to feel. A clock placed at the equator, where the Earth's surface moves fastest, runs just a little bit slower than a clock placed at the still point of the poles. The difference is impossibly small, a few billionths of a second each day. but it is real. Your phone's navigation system must account for this truth every moment. The satellites high above us, moving at thousands of miles an hour in a place where gravity is weaker, experience time differently. Their onboard atomic clocks tick faster. And if we did not adjust for this, for the gentle curvature of space-time caused by Earth's spin and mass, our maps would lead us astray within hours. Every time we find our way, we are listening to the universe's quiet rules, following a map drawn by gravity, motion, and spin. So who started this spin in the first place? Who keeps it turning? The universe whispers that no one must. The answer traces back to the beginning of our solar system, to a vast, cold cloud of gas and dust that began to collapse under its own gravity. As it shrank, it began to spin faster, just like a skater pulling in her arms. That single primordial motion was distributed to everything that formed within it, to the sun, to the planets, to their moons. Each body still carries a fragment of that ancient rotation. No outside force keeps them spinning. They continue because of inertia, because an object in motion remains in motion. In the near-perfect vacuum of space, where there is almost no friction, a spin can last for billions of years. It continues because it remembers. The relationship between spin and time grows stranger and more beautiful the deeper we look. On the planetary scale, spin defines our days. On the cosmic scale, it drags time itself. And all these levels are connected by the same quiet law. Motion is conserved. Time, in this sense, is not a separate thing. It is a reflection of how motion and energy interact. Our entire galaxy rotates once every 230 million years, carrying the sun and all its planets in a vast, silent spiral. Each star's orbit is a tick on a grand cosmic timepiece. One rotation marks the rhythm of galactic time. Just as the atom's spin defines our seconds, the star's spin defines the eons. And so we might say that time itself is recorded in motion. The second is written in the hum of the atom. The day is written in the turn of the planet. The cosmic epoch is written in the spiraling of the galaxy. Everything that moves measures, and everything that measures moves. So if spin governs time and spin itself arises from the natural conservation of motion, then who or what controls it? The most precise answer science can offer is that the universe controls itself. Every spin is balanced by another. Every slowing motion is matched by a quiet exchange of momentum somewhere else. The laws of motion do not change. The universe runs on balance. What is lost in one place is gained in another. There is no master clock, no hidden hand. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope, its quiet built-in way of keeping everything aligned. From your atoms to the stars above, the same principle governs every scale. Take a breath. The atoms within you spin in harmony with the turning Earth, the orbiting moon, the spiraling galaxy. You are already part of that motion. Every heartbeat a fraction of a universal rhythm that began long before clocks or calendars or light itself. And as that rhythm continues, another question slowly rises. If the universe depends on perfect balance, what happens when that symmetry breaks? If everything had once been perfectly balanced, nothing would ever have moved. There would be no stars, no atoms, no time. Only a profound and endless stillness, unchanging and eternal. But the universe we know began not with perfection, but with a tiny imperfection. A small, quiet crack in the symmetry of the beginning, a single flaw that allowed everything to unfold. In the language of physics, symmetry means that the laws of nature are the same in every direction at every point for every observer. When this symmetry holds perfectly, nothing has a reason to change. But when it breaks even by the smallest amount, motion appears. Structure emerges, and time gains a direction. The universe as we know it exists because that perfect symmetry did not last. Let us drift back again to the first fractions of a second after the beginning. The early universe was a hot, dense, and perfectly unified place. The fundamental forces that now govern everything were once a single, seamless whole. But as the universe expanded and cooled, these forces began to separate one by one. This process, a gentle breaking of that original symmetry, shaped everything that was to come, from the structure of the smallest atom to the vast, silent fabric of space-time itself. We can still see the memory of that moment, the faint afterglow of the Big Bang. The cosmic microwave background is astonishingly uniform. It is the same temperature almost everywhere we look. Almost, but not quite. Within that soft, ancient light, there are tiny variations, differences in warmth, only one part in 100,000. They are the first recorded signs of that broken symmetry. Those minute fluctuations, those impossibly small differences in energy, later grew under the slow pull of gravity, becoming the seeds of galaxies, of stars, and of planets. Without those tiny imperfections, the universe would have remained a smooth and static mist, endless, featureless, and empty. Even matter itself, the very substance of our world, owes its existence to this broken balance. In the first moments, the universe created matter and its mirror image antimatter in nearly equal amounts. But nearly is the quiet, crucial word. For every billion particles of antimatter, it seems there were 1,000,000,001 particles of matter. A slight, inexplicable imbalance. When the matter and antimatter met, they annihilated each other in a flash of light. But because of that tiny asymmetry, a small fraction of matter survived. That leftover stardust became the stars, the planets, and everything we can see today. This subtle preference, this flaw in the perfect mirror, is a deep truth of our universe. The laws of physics, it turns out, treat matter and antimatter just a little differently. This quiet discovery revealed that the universe is not as symmetrical as it appears. It has a preference. It leans in one direction. In a way, that imperfection is what made everything possible. Without it, the universe would contain no matter, only light. This breaking of symmetry happens in other gentle ways. As the universe cooled, a field of energy that permeates all of space, known as the Higgs field, settled into its present state. It is this field that gives particles their mass, and in doing so, it broke the symmetry between light and matter. It is often said that this field is what froze the universe into its current form, locking in the differences that allowed for complexity, for structure, for a world where things could happen. Even the flow of time may be a memory of a broken symmetry. In the very first instant, time could have flowed equally forward or backward. But a tiny, random fluctuation, perhaps, in the distribution of energy pushed it in one direction. And from that moment on, it has only flowed forward, creating the river of time that we all drift upon. The arrow of time is a result of the universe beginning in a state of high order, a state of broken symmetry that all later moments remember. When we measure time, we are really just measuring how far we have drifted from that original perfect balance. The great cosmic web, the vast structure of filaments that connect all the galaxies, arises from this same imbalance. The deepest images from our telescopes show galaxies forming along invisible threads of dark matter threads that trace the patterns of the earliest quantum fluctuations. What began as tiny random irregularities just moments after the beginning became the architecture of the universe. Without asymmetry, gravity itself would not work the way it does. A perfectly uniform sea of matter would pull equally in all directions, and nothing would move, but with a slight unevenness. Gravity could take hold, drawing matter into clusters, forming galaxies, stars, and eventually us. Even on the smallest scales, particles carry this memory of imbalance. Tiny ghost-like particles called neutrinos all spin in the same left-handed direction. This handedness of the universe is another quiet echo of the original symmetry breaking. It is a pattern that repeats from the tiniest of scales to the largest, from the spin of a subatomic particle to the rotation of a galaxy. Everywhere we look, the universe shows a preference, and this deep cosmic bias, this gentle leaning of the universe, may have even shaped the chemistry of life itself. The molecules that build us also have a handedness, a preference that reflects the same ancient asymmetry written into the fabric of the cosmos. You are living proof of this asymmetry. You are made from the matter that once outnumbered its mirror twin by just 1 in a billion. Every atom in your body carries the trace of that cosmic bias, a memory preserved since the first microseconds of existence. The universe began because symmetry broke, perfection gave way to motion, and motion gave rise to time. A small crack in the balance created everything that would ever spin, shine, or breathe. And as we follow that first imbalance outward, we reach a new puzzle. A question not about beginnings, but about what keeps the cosmos together, despite its restless turning motion. Because when we look out into the great turning expanse of the cosmos, we see a motion that should not be possible. Galaxies spin at impossible speeds. The stars on their outer edges, far from the bright, heavy center, move so fast that by all the laws of gravity we once knew they should fly apart, scattered into the darkness like sparks from a turning wheel. And yet, they do not. Something unseen is holding them in their slow, graceful dance. A silent mass, an invisible gravity that outweighs everything we can see. It is a quiet, steady presence that does not shine or reflect or absorb the light. It does not form atoms or worlds or stars, but it pulls. And that gentle, invisible pull is what keeps entire galaxies from tearing themselves apart. Astronomers have given it a simple, quiet name: dark matter. The mystery began as a whisper in the 1930s. An astronomer named Fritz Zwicky was studying a distant, vast collection of more than 1,000 galaxies, and he noticed something strange. The galaxies were moving too quickly. Their visible mass, all the stars and gas and dust he could see, was not nearly enough to hold them together with gravity. The great cluster of galaxies should have flung itself apart long ago. He suggested there must be an unseen mass there, something else providing the missing gravity. For decades, his idea remained a quiet thought, a puzzle at the edge of astronomy. Until in the 70s, an astronomer named Vera Rubin began to listen to the rotation of individual galaxies. She measured the speed of the stars, and she found something that defied all expectation. Stars far from the galactic center were orbiting just as fast as the stars near the core, according to the laws of gravity. Their speeds should have dropped as they moved outward, just as the farthest planets in our solar system move more slowly than the ones close to the sun. But her measurements showed something different. Every star, from the bright heart of the galaxy to its faintest, most distant edge, moved at nearly the same speed. It was as if something unseen was spread throughout the galaxy, supplying extra gravity everywhere. That unseen something now appears to make up about 85% of all the matter in the universe. It is 5 times more abundant than all the visible matter that makes up the stars, the planets, the clouds of Gid and us. We now believe that galaxies sit inside vast invisible halos of this dark matter, like islands of light in a much larger, unseen ocean. Each halo acts as a kind of scaffolding, a cosmic glue that binds the stars and gas together through its gentle, persistent gravity. Without it, a galaxy like our own Milky Way would unravel in just a few million years. Dark matter is the invisible architecture that allowed the galaxies to form in the first place. In the early universe, it provided the gravitational seeds upon which ordinary matter could gather. It is the shadow universe holding ours in its quiet, invisible grip. And though we cannot see it, we can see the way it bends the light. When light from a very distant galaxy passes near a cluster filled with dark matter, the unseen mass warps the fabric of space-time, and the light follows that curve. It is an effect called gravitational lensing. The dark matter acts like a great cosmic lens, magnifying and distorting the background light into graceful, shimmering arcs. We have seen these arcs with our telescopes. They are the faint, beautiful signature of an invisible presence. We have even seen this dark matter separate from the light. When 2 great clusters of galaxies collided, our telescopes saw the hot gas of ordinary matter slow down in the collision, like a great cosmic cloud. But when we mapped the gravity of the cluster, we found that most of the mass, the dark matter, had passed through the collision without slowing at all. A ghostly presence that feels gravity, but nothing else. It was clear, silent proof that most of the mass in the universe is an independent, unseen thing. What it is, we do not yet know. We only know what it is not. It does not interact with light, which is why it is dark. It interacts only through gravity and perhaps through one of the other fundamental forces in a way so weak we have not yet been able to feel it. In quiet laboratories deep underground, shielded from the noise of the cosmos, we listen for the faintest whisper of a dark matter particle passing through a single rare collision that might finally reveal its nature. So far, the search has been silent, but its presence is felt everywhere. It shapes the great clusters of galaxies. It influences the vast cosmic web. It even affects the way the universe expands in a slow cosmic tug-of-war with another mysterious force, dark energy. Our own Milky Way is held together by this same invisible hand. The Sun orbits the galactic center at over 500,000 miles an hour. At that speed, given all the stars we can see, our galaxy should have torn itself apart long ago. But the great dark matter halo surrounding us adds the necessary mass to keep it whole, a quiet, stable embrace. It is a strange and humbling thought that what keeps the galaxies whole is something we cannot see or touch. Yet, its quiet gravitational melody holds the cosmos in tune. Without it, the universe would lose its shape, its stars flung into the darkness, its great clusters unbound. Dark matter is the quiet architecture of existence, a framework made not of light, but of stability. Take a breath. Every star you have ever seen, every galaxy that drifts across the lens of a telescope is balanced upon something invisible. You are living in a universe held together by shadows, forces that act without being seen, guiding the motion of everything that spins. And as we trace that invisible hand through the darkness, we begin to wonder, could it also have shaped the direction of life itself? Every living thing on Earth is twisted just slightly. Your DNA, the delicate spiraling staircase that holds the blueprint of you, always twists to the right. The amino acids, the tiny building blocks that form every cell in your body, always bend to the left. This one-sidedness is one of the deepest and most quiet mysteries in biology. It means that life, down to its smallest, most fundamental shape, has a preferred direction, a bias, a spin. In the world of chemistry, this is called chirality. It means handedness. Just like your left and right hands are mirror images of each other, but cannot be perfectly aligned, certain molecules can exist in two forms, one left-handed and one right-handed. In the quiet random processes of chemistry, both versions should be created in equal amounts. But in the living world, only one hand is ever chosen. It is as if, long, long ago, life made a permanent decision and has followed that same gentle spin ever since. Why, if chemistry alone has no preference, then something outside of biology, something from the wider universe, must have nudged life toward one side. One possible clue comes from the light of ancient stars. In the early universe, young massive stars gave off intense ultraviolet light. As this light traveled through the vast dusty clouds, that drift between the stars, it could become polarized, its waves beginning to oscillate in a particular direction. This polarized starlight, in its long journey through space, could have selectively destroyed one type of amino acid more than the other. Over millions of years in the cold, quiet nurseries where stars and planets are born, that subtle preference in the light may have seeded the handedness of life itself. We have found evidence for this in the most ancient travelers of our solar system. When a meteorite fell to Earth in '69, scientists found that it carried within it a slight excess of left-handed amino acids. This small rocky messenger from the time before our world was formed carried a chemical fingerprint from the early solar system. And that fingerprint showed that the universe already had a preferred molecular direction, a bias that life would later adopt. It means the direction of life's molecules could have been inherited from interstellar chemistry, a memory shaped by cosmic light and motion long before our planet even formed. This asymmetry may not be an accident. It may be a deep structural harmony. The left-handed amino acids fold into proteins that can bond perfectly with the right-handed nucleic acids of DNA, forming the elegant interlocking chemistry that sustains life. If you reverse the orientation, the chemistry no longer works as efficiently. It is a quiet, perfect fit, a dance between two opposite spins. And this pattern may trace all the way back to the earliest moments of the universe, to the first quantum imbalances, the tiny fluctuations in energy and spin that occurred in the first microseconds after the beginning. We know that some subatomic particles, like the ghost-like neutrinos, always spin in a left-handed direction. This universal handedness, this quiet preference in the laws of physics, shows that even the fundamental forces of nature are not perfectly symmetrical. If the universe's basic forces favor one spin over another, then it is not so hard to imagine that life's molecules too inherited this same cosmic preference. On our own world, this pattern of asymmetry continues everywhere we look. From the slow swirling arms of a hurricane to the delicate spiraling growth of a seashell spin, and asymmetry are built into the design of nature. The farther we look into space, the more this cosmic bias reappears. There seems to be a small but significant difference in the number of galaxies that rotate clockwise versus counterclockwise, a hint of a large-scale directional pattern, perhaps a faint relic of the universe's own early spin. If that is true, then the same quiet asymmetry that governs the turning of the galaxies may echo all the way down to the molecular structures of life. It is a beautiful and humbling thought that the way a galaxy turns might be connected to the way your DNA twists. It is easy to forget that light itself carries a spin. Photons of light can have a right-handed or a left-handed polarization, a kind of angular momentum that affects how they interact with the world. When the light from the first stars passed through the magnetic fields of the early universe fields that were themselves twisted by rotation, that spin could have been imprinted onto the molecules the light touched. Even the simplest grains of dust drifting in the silence between the stars could have been shaped by this gentle cosmic preference, scattering the light in a way that favored one molecular hand over the other. So when we ask whether the universe's spin decided the direction of life, the evidence points to a quiet yes. From the turning of the galaxies to the handedness of the smallest particles, from the polarized light of ancient stars to the chiral molecules of life, every scale of nature seems to prefer a motion in one direction. It is as if life is not random at all, but a quiet continuation of the universe's earliest rotation, a memory written into every strand of our being. We are made not only of stardust, but of the spin of that stardust, the angular memory of its light. Take a quiet breath. Every cell inside you still carries that twist, a microscopic echo of the universe's turning. From the great slow dance of the galaxies to the silent spiral of your DNA, the same motion continues smooth and unbroken across billions of years. And as we look deeper into that cosmic connection, another question emerges. Not about beginnings, but about endings. If everything that spins must one day slow, what happens when the universe itself forgets how to turn? Every rotation, it seems, eventually slows. The Earth's days imperceptibly are getting longer. The great graceful spirals of the galaxies are slowly unwinding as they drift apart. Even the stars themselves, those bright furnaces of motion and light, are burning down one by one. The universe that began with a great and sudden spin seems in the long, slow arc of time to be returning to a deep and final stillness. But can motion truly vanish? Or does it simply fade, spreading thinner and thinner across the quiet fabric of space until it becomes a whisper too soft to hear? Energy, a physicist once said, does not disappear. It disperses. And so it is with spin. It does not stop. It diffuses. Our own planet is already losing its rhythm. Each century, the moon's gravitational pull, a quiet conversation across the darkness, slows the Earth's rotation by the smallest of moments. And as it does, it takes a little of our planet's turning energy for itself, causing it to drift just a little farther away. It is a gentle cosmic dance that has lasted for billions of years. A slow, steady unwinding. If this continues, the Earth's rotation will one day lock with the moon's orbit, and our world will always show the same face to its companion, just as the moon already does to us. It will be the end of the tides, as we know them, the end of the daily cycle of ocean and air. A planetary spin, once so vibrant, will fade into a silent, perfect equilibrium. Elsewhere in our solar system, the same quiet story plays out. Venus, wrapped in its dense atmosphere, has slowed to an almost unearthly crawl, its day longer than its year. Even Mars, whose rhythm is so much like our own, is gradually, imperceptibly losing its speed. Over the vast, slow scales of cosmic time, spin is not forever. It is a rhythm that is winding down. This slowing continues beyond the worlds we know, out into the heart of the galaxies. When we look at the most distant ancient galaxies, we see that they once spun faster. Their arms were tighter, their cores denser, their motion more vibrant. As time passes, the gentle friction of cosmic expansion and the slow dance of gravity gradually sap that motion. When two galaxies meet, their stars rarely collide, but their great invisible halos of dark matter interact, and their spin is redistributed outward into the quiet space between them. This process leaves the galaxies rounder, slower, and more diffuse. The bright, sharp spiral gives way to the soft, quiet ellipse. Eventually, the Milky Way and our neighbor Andromeda will meet not in a great and sudden chaos, but in a slow, silent fusion. Their combined spin will settle, softening into a single, massive, nearly motionless glow. But spin does not vanish when the stars fade. It transforms. When a great star dies, it collapses inward. And in that collapse, it conserves its ancient motion, spinning faster and faster until a star, once millions of miles wide, becomes an object the size of a city, rotating hundreds of times every second. These are the neutron stars, the pulsars, the final brilliant flare of a star's spin. Yet even these cosmic lighthouses eventually slow, radiating their energy away into the darkness, their powerful beams fading into a final quiet pulse. And as time expands, further rotation becomes scarce. The stars have all gone out, and the black holes, the last great engines of spin, also begin to fade. They slowly evaporate, leaking their energy back into the universe over unimaginable timescales. A spinning black hole gradually transfers its rotation to the space around it, releasing faint ripples, gravitational whispers that stretch across the quiet dark. Even when the black holes themselves are gone, their rotational memory will remain imprinted in the very geometry of the universe. So will the universe ever truly stop spinning? Not completely. The laws of physics tell us that angular momentum, The memory of motion can never be destroyed. It can only be spread thinner shred among an ever-expanding sea of faint, lonely particles. The universe, in this sense, never stops moving. It only redistributes its motion until it becomes imperceptible. There may come a time in the far, far future when the universe enters what is called its heat death, an age when all energy is evenly distributed. There will be no warmth, no light, no flow, no reason for anything to move. Rotation will still exist as a mathematical truth, but without contrast or structure, it will have no meaning. It will be a cosmic silence, a final, perfect calm after every vibration, every orbit, every spin. Even so, the spin will leave fingerprints that can never be erased. From the faint polarization of the first light to the gentle curvature of space-time around a dying star, the memory of motion will remain encoded in the universe's design. It is not the movement we lose, only the strength to notice it. Take a long, slow breath. Right now, the Earth's core still turns, the stars still orbit, and the Milky Way still drifts through the darkness. Every motion you know is a flicker of that ancient rotation, one that will outlast you, but not eternity. And when that eternity arrives, when the last spin finally stretches into silence, something else will still remain. Not movement, but the memory of movement. Because even when the universe forgets how to turn its geometry, we'll still remember that it once did. And as we approach that horizon of stillness, another question quietly unfolds. If every atom, every planet, every galaxy is slowing down, what does that make us? The ones still moving within it. Every atom inside you is spinning. The electrons that hum in their quiet orbits around your nuclei. The protons and neutrons held deep within them. The quarks that exist in a place even deeper still. All are caught in a ceaseless, gentle motion. And that motion is not random. It is a continuation. It is the faint, unbroken echo of the universe's first rotation. When you move, when you breathe, when your heart beats, you are not separate from the cosmos. You are part of its oldest memory. In the quiet language of physics, the persistence of spin is called the conservation of angular momentum. It is the simple, elegant rule that keeps motion alive. It is why the galaxies still turn, why the planets still orbit, and why the atoms inside you still vibrate after 13.8 billion years. This ancient motion cannot be destroyed. It can only be transferred or shared. That means every spin in the universe, from the grandest swirl of a galaxy to the smallest quantum hum of a particle is a continuation of the same original turning that began at the very start of time. That primordial spin never vanished. It fragmented, spreading across all scales. It became the great slow turn of the galaxies. It became the faster spin of the stars as they form from collapsing clouds of dust. It became the orbits of the planets that gathered in the disks around those stars. And within those planets, inside every rock, every ocean, and every living cell, the pattern continued, echoing downward into smaller and smaller scales. Our atoms, too, hold this rotational memory. The electrons that define the shape and feel of our world obey the quantum property of spin, a fundamental internal angular momentum. This is the quiet engine of atomic structure, the silent law that creates the difference between chaos and stability. Without it, chemistry would not exist. There would be no bonds between atoms, no molecules, no water, no air, no you. In this sense, you could say that every piece of matter carries within it an ancient choreography. The spin of these tiny particles leads to the magnetic fields that shape our world fields, that guide the stars, and fields that allow for the possibility of life. Your own neurons fire using electrical potentials that are shaped by these same timeless principles. Every thought that drifts across your mind is an alignment of charged particles, a kind of ordered, gentle motion. And so when we ask whether we might be the universe remembering its own movement, the question is not just a poetic one. It is physical. Each brainwave, each quiet signal in your mind is built upon the foundation of rotations that have existed since the dawn of time. In a scientific sense, memory is a form of pattern preservation. It is information encoded in a physical state. Atoms remember through their spin. Cells remember through their molecular structure. And the universe remembers through the very geometry of space-time itself. Every movement, every rotation leaves a small, gentle indentation, a swirl in the fabric of reality. Your own movements, though infinitesimally small, also disturb space-time ever so slightly. The difference is only one of scale. The atoms in your body spin billions of times per second, and each of those micro-rotations contributes to the ongoing, unbroken record of motion that began long before we were here to notice it. If all motion leaves a trace, then perhaps what we call awareness is simply the universe's way of perceiving those traces through us. Not as a spirit or a soul, but as a physical continuity, as matter recognizing its own persistence. Even the light from the stars, the gentle messenger of the cosmos, carries this memory. Photons of light have their own spin, their own angular momentum, which determines how they travel and interact with the world. The oldest light in the universe, the faint afterglow of the beginning, carries the most ancient record of this rotational memory. So when you gaze at the starlight on a clear night, you are literally seeing the memory of spin. You are seeing light that has been twisted and stretched by billions of years of motion. And that light enters your eyes, triggers a quiet chemical reaction, and becomes part of your own neural motion. In that way, the universe does not just remember its spin, it continues to experience it through every observer it creates. And even as the cosmos expands and cools, these traces will persist. The galaxies may slow, their bright lights may fade, but their angular momentum will never disappear. It will be passed on to the thin cold gas between the galaxies, to the great dark matter halos, to the faint radiation that will fill the final darkness. The patterns will remain. The memory of motion preserved as geometry. The cosmos is within us. We are made of stardust. We are a way for the universe to know itself. In the quiet language of physics, that knowing happens through motion, through energy, and through spin. The universe is continuously encoding and retrieving its own long, silent history. Take a breath slowly. Every atom inside you continues to turn with the same ancient spin that once ignited the first stars. You are a moving archive, a living part of the universe's ongoing memory. And perhaps what we call life is just the brief, quiet moment when the universe pauses just long enough to notice that it is still spinning. If this quiet journey has brought you even a small moment of peace, I'm deeply grateful you have spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It is what keeps me creating these cosmic lullabies for wandering minds like yours. And if you're kind enough, please tell me in the comments where you are tonight and what time it is where you're listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they are like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe turn softly around you.